So welcome to another video on policy-based reinforcement learning, and in this video we will introduce deep deterministic policy gradient, Ddpg. So while we introduced policy gradient methods such as vanilla policy gradient, Monte Carlo policy gradient, PPO, TRPO, the question is, can we also leverage ideas from value-based reinforcement learning for continuous action spaces? So we actually ended our value-based reinforcement learning videos with DQNs, where we then actually introduced policy gradient methods to actually have continuous action spaces, which was the main limitations until DQNs. And the question is, how can we actually leverage ideas from value-based reinforcement learning also for continuous action spaces? So it boils down to the question, why can't we use just Q-learning and DQNs for continuous action spaces? And what you might have also guessed is this is not that easily being done, because actually if you remember how we actually defined DQNs, what was the actual or the original problems that we had with Q-learning? And the thing is that Q-learning and variants, including those like DQNs, they do not work with continuous action spaces. And why is that? Remember that we actually calculated the targets of our Q values in the update function of our time difference learning target using this equation. And this was actually the Q-learning target. Doesn't matter if it's like for continuous state spaces or not, but however it requires we just took the one-step return and then used the discounted value of the maximum Q value of the upcoming state. And the problem is that we have this max operation over the Q values. And in DQN, we just use a single pass through our network, and we had static times the number of actions outputs that are actually our Q values, and then we could just select the maximum Q value to actually estimate the target that we are using to bootstrap our Q function. And however, it now turns out, so what we actually did is we defined the Q function like this, that we had a single input as a state, and then we had number of action outputs. And the question is, how can we actually come up with a Q function that provides a continuous output? And however, which actually would mean that we would actually have a Q function that takes as an input S and A and provides a continuous output. What is actually something that we could do, but we did not really focus on. However, what we have seen is that if we would really have like continuous action spaces, and this would also be the input to our neural network, evaluating a continuous action space to actually get a maximum Q value for a certain state requires something like an exhaustive search over all the available actions, which becomes highly non-trivial in practice. However, there's also work that actually deals with this problem, but it's out of scope for this video. So what is actually the main idea behind Ddpg? So in Ddpg, we actually learn a Q function and a policy jointly, which means that we're using off-policy data plus a Bellman equation to learn the Q function, as we have seen it in Q-learning as well. And then we make use of our Q function to learn the policy. And the basic intuition behind Ddpg relies on the idea of Q-learning. So if we actually know then the ideal Q function, then in each state the optimal action that we can take is simply be found by taking the argmax of our Q function. So this is actually the idea we also use in Ddpg, and this is the general Q-learning idea. And Ddpg jointly learns approximations to our Q function and our optimal action for a certain state S. And is specifically adapted for continuous action spaces, means that in turn it needs also continuous action spaces, and the Q function needs to be differentiable with respect to our actions. This is actually some side constraints of Ddpg, which however are not that critical in practice. Okay, so what is the main idea behind Ddpg? So we actually assume that our Q function is differentiable with respect to A, meaning that a slightly change in A also tells us the derivative or the gradient direction of Q. And this actually allows for a gradient-based learning rule for a policy mu of S that actually exploits this information. So meaning that instead of actually exhaustively looking for our max Q as A, we just use a policy network to approximate this value. This is the general idea. So we just, next to our Q function, learn a policy function which is actually approximating the maximum Q value. So we can just say that we find a function approximator that approximates this function. And if we formulate the problem like this, we just need to look at two sides of Ddpg, and the first side is actually the Q-learning side, and the second side is actually the policy gradient side. So let's just look at the Q-learning side of Ddpg first. To actually boil this down, just recap the Bellman optimality equation. That is what we actually wanted to learn. So this is the Bellman optimality equation that you also know from early videos of this year's reinforcement learning class. And Q-learning, so the optimal Q-learning just says that if we have the optimal Q function, then the expected, so if we follow our policy and our distribution, the optimal Q function just satisfies this equation, which basically says that the Q of SA is nothing else than if we take this action and we get the reward, it is this reward plus the discounted maximum Q value of the successor state. And actually, what we then did is, or if we have this, we just optimize the mean squared Bellman error with neural network parameters pi and given a set of transitions D. And this is just some formulation of Ddpg that does not look, let's not focus on this one, but we can just formulate our Q-learning target like this, which is actually what we also did somehow in DQNs. And this is actually what we also can do in Ddpg. So we want to just use this optimization target, and we can also apply things like replay buffers to make it work off policy, and use target networks that in this case are not like hard reset and copied, but done with something like a polyarc update, meaning that we just copy a portion of the old parameters over the new parameters every once in a while. Okay, so now the real question is, how can we calculate the max over the actions in the target function? So this is actually the non-trivial part in here, and turns out that, let's just do it like this. Let's just say that we have a target policy network mu that actually computes an action that approximately maximizes the Q target. So nothing else than we have next to our Q function a policy network that tells us the Q value of the maximal state of the maximum action at a certain state. So if we have this, we can just plug the output of this policy network in here, and this actually helps us to evaluate the Q target of our Q function, and then to have the whole update rule for our Q function. It turns out that if our Q function is differentiable with respect to our action, this actually can be learned end to end, and we can actually use the output of our policy network to get the Q target for our Q network. And then we can just use stochastic gradient descent to actually update through a set of through a bunch of parameters. We can just update our Q function. So this is actually the Q learning side of Ddpg, and there's also the policy learning side of Ddpg. And turns out that while you might think that in the first place this might be the harder part of both, turns out that they are not that it is not that critical, because actually still our policy mu is a deterministic one. So we just get a Q value, and it actually says that our policy is just defined in a way that we say that the mu theta of S just returns that action, the action that maximizes our Q function, and if we would put this action inside our Q function, we would get the Q value of this action. So if the action space is continuous and we assume actually Q to be differentiable with respect to the actions, we can also use gradient ascent actually with respect to the policy parameters and actually optimize our policy function. So this is actually what we can do. And in this case, our Q function would just be a frozen network, and we can optimize our policy parameters to actually come up with an action that maximizes the return. So this is the idea behind DDPG. One thing to mention at this point for DDPG is DDPG has some or needs to take account a little bit exploration exploitation in this case. So DDPG actually trains as an off-policy algorithm, while the policy is a deterministic policy, meaning that there is no randomness involved in selecting the actions. Hence, on-policy exploration trained on off-policy data is usually not enough, and a usual solution to actually account for this is to add noise on the action during training time. So what you usually do is we just add some noise factor on the actions, and that introduces some randomness so that we actually explore well enough. Originally, the DDPG paper suggested something to use time-correlated Ornstein-Uhlenbeck noise. However, more recent work just resorts to zero-mean Gaussian noise, as this is much simpler to implement and exhibits something like same performance, and is also much better understood in practice. As you would also suggest it, or as you also might have thought, over the course of training, you reduce usually the scale of the noise, so that you actually go down to a deterministic policy, and at test time you of course omit the noise completely, because you actually want to act greedily with respect to your policy. So this is actually the pseudocode of DDPG. It's also implemented very simple. So you have some initialization in the beginning, where you actually have target networks as you also know them from DQNs, for both the actor and the critic, so the Q function and the policy function. And so here you have your random process, which is actually something which I defined in the previous slide, where you actually define a stochastic policy. Because you do not have a stochastic policy, you define a random process to actually incentivize exploration. And then you keep on doing your training procedure, where you actually go over a certain time step, and you do like what you know from Q learning and in DQNs. You execute actions, you observe rewards and put them in the memory, where you actually lay the sample from. What you then do is you actually update your critic network by minimizing the mean squared Bellman error loss using the action proposed by your policy network in here to actually get your Q learning target. And if you did this, you update your actor policy using usual policy gradient, in this case the deterministic policy gradient theorem. So if you're interested, look into this one. But this is like the policy gradient update, and every once in a while, or in this case every iteration, you update your target networks using a poly upgrade. This is DDPG. In summary, DDPG is something like a special case of an actor-critic algorithm. It only works, in contrast to other algorithms, it only works for continuous action spaces. It is actually an off-policy algorithm, which is very nice in practice, and it utilizes all the replay buffer tricks and things like this that you also know from DQNs. And it solves deterministic policies instead of stochastic policies. Some pros and cons. DDPG it produces impressive results both in simulation and in real-world problems. It's one of the de facto standard algorithms to use for continuous or very large action spaces. However, it is very sensitive to exploration process, so actually define the exploration process, and it's not implicitly being guaranteed by the stochasticity of the policy, because it is a deterministic policy, which also makes it very hard to be tuned in practice. So actually it's in contrast to other policy gradient algorithms, which are not that sensitive to hyperparameters in DDPG, you need to tune them a lot to actually get a good combination of hyperparameters and to let DDPG work well. And compared to other octocritic algorithms, it's slower in terms of wall clock time. So it's not in terms of sample efficiency, but in terms of wall clock time. Of course, because you're actually training more and you resort to your replay buffer, of course you use more wall clock time for training of your RL agent.